Okay, for some reason I deleted the video I just spent 20 minutes making for you guys on the same subject, so this will be an accelerated process version of it again. Irritated version a little bit. Let's go into it. So if you engineers that look at this and say it's going to collapse, it's going to collapse. All right, I want you to think of this. How do you turn this steel into post-tensioning steel? How does that become post-tensioning steel? Engineers out there going, you're crazy. It's not post-tensioning steel. It's just rebar. All right. Well, it's pretty much not active now. It's got some engagement right here. And this one too. Limited. You can't just grab it from the end here and just pull it out, off the surface here. If you were to cut it all here, can you just grab this and pull it that direction? Not really, because you have concrete out here. All right, we have concrete out here, so we can't grab it from there. So we'd have to cut it here and here to remove the pieces of steel. So what does that mean? That means here's the wall surface. That means we have it anchored back here. So this becomes an anchor point. This is a fast video now because I'm pissed that I'm doing it twice. And since you see no fractures there, that's also an anchor point. So now as you're looking at this steel, you see that we have anchorage going through. So I'm going to literally draw down the steel and tie it into the anchor points. All right, it's consistent in spacing. It looks pretty darn good. I don't know what I'm doing there between there, but I'll just leave it like that. Okay, so it's consistently doing good. Let's look at the reinforcement. The reinforcement still has its ribs on it, if you will, the deformations. However, each designer of each manufacturer will reference it as different. Even some designers call them teeth, manufacturers. So the engagements at your wall, roughly at your wall area here, and one engineer on TikTok stated that she's doing the assumption that the deck stops here. The assumption is the deck does not stop there, that the reinforcement goes through the deck into the slabs internally. Okay, so this is the top steel we're looking at. So we have anchorage left and right. As you can see, this area here is not fractured. Some locations it may be. You're looking at it from the side there. You may see rebar here, the top steel. And then you see this fractured here. Then looking at the deck, you look back for the part that's not broken, and you might get it back here. So that moves the anchorage point inbound a bit. With that said, what we're proposing here is that 3 foot of this deck off this wall be the travel zone area. That 10 pounds on a cantilever out here is puts a greater stress on this balcony than 10 pounds over here within a 3 foot zone. I'm going to delete all this now in a moment. But I want you to note at that steel. I want you can see the scab piece they put on there, little scab they put on top of there. It looks like a grout material. It doesn't look like a real concrete type material. I could literally remove that and see what's underneath of it to see if they put it on top of loose debris. Incidentally, I would not recommend removing that loose debris. That loose debris would be troublesome, and that you could not trust a person to remove it without the deck being supported first. I would rather it be supported. I would not want to see a single chipping hammer up here until the deck is fully supported, and then maybe not. I don't like the idea of them possibly jackhammering here, fracturing the rebar, or sending vibration down this rebar into the structure and causing issues. We would not want that. So this is a very delicate, professionally removed loose debris surface. They may then get a CSA type product on it, which hardens in about an hour. It's not structural at that point. It's the load bearing is on the floor below. This is a wear layer, and then it will get this beautiful product that's vinyl, heavy duty vinyl that will protect it. Commercially, they state the product is 15 years. So 15 years is a great life cycle for a new wear layer, or it can be a very, thought out process of coatings that you can apply on top of here, that no fracture that you observe, that you would not have the fractures. Now let's go ahead and draw the cantilever in a profile there. This will be literally the deck. It's tied around there. This is the railing going up, all right? It's also your force. You want to think of the 10 pounds I told you about out here, and this creates that rotation effect. Now there's a young engineer. She's on TikTok doing videos on this. She states that for concrete to work, it must be in compression on all sides. If that was true, then Newton is wrong, because Newton says equal and opposite reactions. And by you saying it must maintain compression on all sides, you're not, the opposite of compression is tension. Where's your tension in your theoretical thinking of how concrete works? You also state that rebar is just like a binder. Rebar is not a binder. It has an ability to resist deflection, is what it has an ability. It's not a binder. All right, your binder is your paste, your mortar of whatever design you come up with. All right, so now let me do the top steel. So let's do this top steel, and the engineer online, she stated she's 28 years old, so I'm going to give her that. And I'm not mansplaining, I'm engineer-splaining, okay? So I know she likes to, I saw her videos, and I'm trying to communicate with her, but just so she knows, I'm not soft. I don't know how to be a simp. I'm not one, so I just call it, tough shit. So you state that your assumption is that it stops at the building, the load stops at the building, that the balcony stops at the building. That assumption is wrong. The building platform, the balconies go into the structure, as well as the steel. The bottom steel, is some bottom steel there also. So we have bottom steel and top steel. We have our force down. Now this will be visualized as rotating if it was falling down. There's already a pitch, an existing pitch on this deck that for water runoff. All right, existing pitch as per one of the engineers that inspected this deck informed me. Now I'm going to do this, and if this was to rotate down like that, you would start seeing an opening here, an opening here. My zone, my anchor zones, remember I said post-tension, how I would talk about how I get post-tension bars out of this, is that these middle sections are anchored. These are anchor points. This is an anchor, and out here's an anchor. These are anchor points, and between tying the two anchor points in, like post-tension rods, are the rebar. The rebar is now, because it's not really doing too much there, it's now working an anchor point to keep this cantilever from rotating over. So now they're working in that capacity that I'm going to do another color. Let's go red. So let's call this the anchor zone, and this the anchor zone. And you can see your rebar anchorage is here. I'm going to underline it and do that like that. And your anchorage is here. The top steel anchored back at the wall into the structure, going back, stops this rotation from taking place because of the anchor points, that this is still nice out here. Some places it is swollen and its anchor point moves in a bit. That's why I proposed 3 foot to the wall. The bottom steel is it goes under compression. Unlike most people will tell you that bottom of the concrete is in tension and the top part is in compression. Not in this case, not in a cantilever fashion. And a cantilever, this top steel is your tension steel. So you can come down here and you can start wringing this, grabbing it with your fingers, seeing how tight it is or not. You may be surprised. This one may be loose. This one may be taut. This may be taut. This may be loose. So loose, taut, taut. And I showed that with a bridge that had suspension bridges, small, pretty wooden suspension bridge that uses post-tension bars to support the structure. Around 100 plus degrees that day that I was out on the structure, I showed that the bars, a few of the bars were loose. I could grab them and they were just loose. and the bars right next to them were tight as can be. So let's do a mini version. So here's the bridge, and these bars are coming down like this. These bars, a couple of them were loose bars, and then this one was tight as hell, and another one's tight as hell. So under temperature changes, those became loose, and so the load therefore is now transferred in this bottom tie beam from this one to the next tight one. These two are loose, are not taking on the loads. So is that intent? The finite element program, did it show that? Did the engineer intend that this decking can take this now new unsupported span from here to here? Not with the two bars participating. Did they take that into consideration? This is the true world of behaviors that can take place. So this steel here is tension. It becomes a tension bar, no longer the reinforcement as it may want to see. Now, everyone there speculates it's salt and slurry and including swelling of the rebar. This could be time, and with 60 plus years, we don't know what went on there. Was there some bouncing parties going on there at one point? Boom, boom, boom. That's shock loading. Shock loading can cause these fractures, and then you go to patch them over the years, and you're doing nothing. You're not going anywhere. So we don't know. This is 60 plus years, built in 1966. 60 plus years, and you can imagine that this is how many parties they might have had out on his deck, and how many people were at the edge of the deck observing it, putting more of that load out here, which could cause some slight deflection reactions and causing the reaction, so that move it in here now, causing this to deflect. And once the load is off, it's too late. You've already spoiled the concrete. I kind of like that because I'm looking at these ribs and I see ribs. All right. I see ghosts. I see ribs. You getting hungry yet? Seeing those ribs? Now let me show you something. So this is a piece of rebar that I put out in the elements for years, approximately 4 years. And this rebar, without being no salts or anything on it, just on top on an upper elevated surface, this rebar deteriorated to that capacity, just being exposed to the air. And then I coated it now with primer to stop it. I want to see if it flakes or not. Just the regular cheap $1 can of primer. Nothing expensive, cheap primer. Very cheap primer. And I don't see the primer flaking off, short of a couple places where I rubbed it. On the other end, I left it exposed here, so this is exposed steel. And on this end, I used a cheap can of dollar paint. I'm sorry, that's expensive primer. On the other end, here's the dollar paint. The dollar can, now it's $2. Everything expensive. This end, you can see the ribs again. This is working on 8 years now, this piece being exposed like this. The covering is working on 2 years. So I coated it about 2 years ago to see what would happen if just exposed with a cheap paint. Would that stop what I observed flaking or not? Now, handling it, showing it to other engineers causes some abrasions and things like that. But that's what that looks like compared to this. This is important that I bent this because I wanted to put, this now has been tensioned. This steel has been deformed. The back rib has been formed in tension. And the internal side of this rib has been put in compression. And so I wanted to observe whether microfractures and things like that developed in the inside, compression fractures, or micro tension fractures on the outside develop and migrate and get larger. This is, I should be able to hand this down to somebody in a will. But this is still observing. Okay, I lost I did something there. Hold on. So I'm still observing this for the behaviors of it, of the steel. Now, steel is not just steel. You just don't have one piece of element in here. You've got multiple composites of materials that were smeltered, and they made this in a mold. And it's dangerous as hell how they make this, how they make it in other countries anyway. It's amazing to watch it whip this stuff when it's hot, whip it around and toss it around. And, it would just slice right through you at that temperature. The and you can see there's some loss of dimension here with ribs showing, but loss of dimensions. Back to the video. So as we look here, measuring it would count. As you look at those ribs to determine whether those ribs are how much they lose. But over here, we see engagement. This one's got a fracture down the line of it. This looks like a control joint here. So it would make sense that it would do something like that. There's also some cross steel going across here, tying all this together. And we know it's active and working. It's working, rather, because we don't see any elevation changes here, not one high, one low. Even at this terribly spalled area, we observe flatness at the seam. So that means the steel that's going this direction, the transfer steel, if you will, is actually working in a redundancy factor to make this work. Now let's go back to the cantilever effect again. So we're going to cantilever it. I'm going to put the railing here, but I'm going to put an arrow down and rotation force there. I'm going to put steel back into here, put steel at the bottom. So the bottom, if it tries to rotate, we would see fractures over here at the wall, more than likely, maybe even out here, some like we see there, maybe the party deck in the 1970s. They won an event and they went crazy. I don't know. I don't know when this started, but it didn't start. This is greater than 6 years before the current owner took over. Again, he was, as I understand it, just, some people got money to invest. He invested and was hoping that the investment partner would do his share and maintain the structure with the help of the management companies, which you expect that management companies would say, hey, we need to do X, Y, and Z. But apparently the multiple or management companies bailed for one reason or another. Which, imagine if you imagine if you just had money and you want to invest it and it was here. You don't want to live here. You just want to invest here. So you hire a professional company, management company, to take care of your interests, including anything that may happen. All right. Everything from fire to evictions, and including this, of course, obviously trip hazards they should know about. This should not be visible at this point. This is a surprise to the owner because the owner is not kept. You don't want to be known day to day. Hey, look, Tom gave me an email today. He's complaining about his room, that he has a leak in his shower or something like that, and then faucet. That's not why you hire a management company, so they can write you those daily stuff like that. You hire them to make you profitable and work and protect your interests. Apparently, these management companies and or partner were, didn't stay on top of this. Back to the anchoring. This is how it becomes the post-tensioning steel. So I'm going to do this again. Your anchorage is here, coming across, and then anchorage. All right. These are your live ends. Your live ends times 2, I would guess. No dead end on this one. Nah, I'd consider this probably the live end. And I'd probably consider this the dead end if I was going to think post-tensioning. What do you got? What say you, the engineers? You like that thinking? I'm thinking this is where we have our wall system. So we're going to have the pad come over. And when it comes over, it's going to have that negative effect. And then we have our different reaction down there. And then internally, we'll have a pad internally that's reacting on the steel also as more of an anchorage. And we have no anchorage out here. No anchorage out there besides the live end, besides the anchorage of the concrete. And what stops from rotating over is the concrete. Let's do this. What stops from rotating over? Let's do this. Wall, steel, anchorage, live end, bottom steel, mostly compressive. But it also takes the transfer steel that goes the other way, probably somewhere out there. Maybe they put it there. Maybe it's further up. Maybe it's under here and we just can't see it yet. Maybe it's just a touch under the ground there. But let's do that. I'm not assuming it's 2 layers. Assuming it's 1 layer of cross steel. I did see it out here at the edge at one of the locations. So that's why I stated it's there. So this matters. This distance from here to here, your thickness of your deck matters, because that force that is trying to compress as this rotates down, that larger deck works in your favor for rigidity. A more scaled, smaller deck will want to fracture along this plane, let's just say right here, in the anchor zone. This one is out here. So we've got the salts, etc., the slurries out there that over time that did some work on this deck. We have the rebar that I say looks pretty damn good. Now let me show you a model of the factor I'm talking about with how it matters if the deck is thin or if the deck is thick like that. And I'll show you a post-tension bar model. I did this in another video, but this one will get it too. And hopefully I don't mess this up by not recording anymore. So here's my deck model that made it through one winter, which is good. You can see it's a little twisted there. But now, this is just rebar, right? Goes all the way through. Thread all. There's my anchor point. I can, of course, tighten this bolt up, nut it back here, and take care of this gap here. But I don't want to. Well, I can tighten this one up out here and take care of that gap. But let's look at this as the deck. And that's the thickness of it. You can see if it was rotating down, we would start getting an opening here. As I push it closer to the structure with tightening up the bolt, if I wanted to, it now gets flat. So that rebar is inside here, the rebar. This thread all is just a drilled hole through there. All right, you can't see it. You can't see it, but it's just drilled in there. It's not, I should be able to spin this. It's nothing, no extra epoxy or anything else added here. So you can imagine if I cut a section out here down to the rebar here, and I cut a section out here down to the rebar, we now have our anchor points here and here, and the deck would still work. This being the concrete below, also it has rebar transferring it. Let's see if I can find my Sawzall quick enough to cut this down to the surface to give you that without screwing this video up. Oops, hammer. So before doing this, I'm going to show you this capacity, so I can load it down with my left hand. Loading down works great. What happens when I make it dimensionally only that thick, like that? Now all of a sudden, look at the loading. It just becomes a springboard. So a springboard. So the bottom of that, as you see, is no steel there at all. It goes under compression back to the wall. It's now functional. It helps out with that loading. Now let me see if I can get this done for you. So now I'll bring your attention to 45-pound weight on the end of the structure, if you will. Exposed rebar between the two, between our anchor point. In this case, we just got a single anchor point, the nut. I'm sorry. But the value of whatever's left behind of that steel going in there, that's your anchor point. This is totally exposed in the middle, and yet we don't see this just falling away to nowhere. Again, because this becomes a compression. If I were to scale this and turn it the other way, that means I'd have to lose the bottom compressive action of it. Let's see if I can come here for better lighting for you. Then I would be, then it would start, well, if this was overloading out there, this would start spalling here and opening up here. But it's not opening up there, and it's not spalling here. It's the rebar appears to be pretty much flat. Again, you got your anchor points. This acts like a post-tension bar now between it, from anchor point to anchor point, until you develop it, the concrete back around it again. But proposing the steel deck pan system, this becomes a redundant system where you don't have to worry about your anchor points again. They're developing your anchor points and making sure this is bonded. If you did do that, I would argue it would be quite costly. I would argue that you'd have to shear link the top steel with the bottom steel for redundancy, because I wouldn't trust just just an anchored bolt into the screwed down anchor bolt into the existing concrete that you would then marry it to it like studs, like Nelson studs. I wouldn't trust that for, you know, I just wouldn't trust it. I like the idea of a new load path and not worrying about the cantilever. 45 pounds, it's a real weight, guys. I'll move it further out. I'll move it further out for you. And load it that way. So there you have it. Okay, so now hopefully this will help you understand what you're looking at, that this part matters, the anchor points. Now some of it is split here, new anchor points develop. You also got transfer steel. If you think of it that way, it's loading around, so like the bridge way I just told you, the bridge I described to you. And well, hopefully this helps you engineers out there, and hope it helps other people understand what's going on. Again, you just can't just put concrete back on top of that and say it's good. The bottom would matter if you saw some fracturing. You might be able to do that and make a drop panel, a larger drop panel, to give it more resistance, more surface area to do that, to handle the loading. But just get rid of it. All right. Oh, there we go. Still loose. No, I didn't do anything trickery. And if I turn this sideways, we still have. So you saw it take that loading. If I turn this dimensionally sideways, I'm in trouble. I'm back to the springboard. Sorry, trying to turn it one hand, hold the camera at the other. I'm back to a springboard. Video. Okay, let's do that again. If it hangs up on the video, so be it. Come on. All right, back to a springboard. So hopefully you understand the importance of it. That compressor part requirement. The anchorage needed. If I would unscrew that, of course, we would get slippage. Starts coming off, fractures, etc. This might be the last video to help you understand this type of what you're looking at, this cantilever deck. So hopefully you enjoy this one, and goodbye.